We still have 1 more minute, but let me pull up the lectures. Okay. Cool. So if you guys are on the course website, today we are going to cover randomized algorithms and QuickSort. This lecture is going to be interesting because most of you said you don't have a statistics background. I tried to add some slides that give what you need to know, but there are going to be things that I'm going to tell you are true, but you might not necessarily have heard before. So to you, you'll just have to be like, okay, that's granted. So when I say linearity of expectation means you can do this step, you guys will just have to be like, okay, I believe you. It might be worth writing some of those terms down and maybe looking them up afterwards if you want to get a little better at the statistics side of things. But yeah, other than that, we are also going to cover a little bit of code in class today. So I do try to put all the resources that I use to create the lectures and also the stuff we cover in class on the website. So if you want to revisit some of the code that we cover, they're linked here on the course website. So I think that should link to the replit, I believe. But cool, let's get started. It is 12 p.m. All right. So everybody knows homework 2 was due yesterday, 11:59 p.m. I saw quite a few submissions, so I'm really excited about that. I also got a few, not as many of you are filling out the feedback forms on the homework, so I'm not getting too much signal, but the people that did fill it out, I think the majority of them said it was just right, which is good. I think homework 3 is going to be in between homework 1 and homework 2. So maybe a little bit more challenging. So just a lot, that's my opinion on homework 3 as I'm developing it. Just a lot that. So if you really struggled with homework 2, you should really come talk to me. If you thought homework 1 was super easy, then homework 3 will probably be a little bit easier than homework 1. So, but it kind of depends because everybody's in a different kind of level, and you guys know different stuff. So homework 3 will be out later today. I did want to get a quick poll from the class. The way we do the homework assignments, they're due on Tuesday at midnight, and then I release the next homework 5 p.m. on Wednesday, or that's what I aim for. How does that work for you guys? I see 1 thumbs up. Yeah, so normally the homework I make it due at midnight on Tuesday. That's you can submit it later, but then you lose points the later you submit it. And then you don't actually have any homework until Wednesday at 5 p.m. when I release the next one. So that means that the amount of time you have to do the homework is not a complete week. You lose those from midnight to 5 p.m. on Wednesday. You actually don't have anything to do for homework wise. That was intentional, but I did get some feedback from students that they actually would like the homework to be released earlier so they can get started on Wednesday morning. I can try to do that. And any opinions, any thoughts? Anybody feel strongly about no? Okay, well, it might change. I think in general, I will aim for 5 p.m. on Wednesday. I will try to get it out earlier if I can, and then it'll just be hey, it's available earlier. If you want to start working on it, go ahead. Cool. Yeah, so that was the poll for homework due dates. So another thing I've noticed, a lot of you, so this is going to be a lot more work on me, so I don't want to necessarily commit to it yet. I want to just ask from the course. Most of the homeworks I'm pretty comfortable in C++, so I draft them in C++. I ask for you guys to write them in C++. I think C++ is a really good language to learn, but the course itself is meant to teach you algorithms, not necessarily teach you any specific language. I just use C++ because I think C++ is pretty good. Okay. What languages are people already familiar with? How many in class know Python? How many are more comfortable with Python than C++? How many are more how many want to keep doing them in C++? Okay. Okay, so it might not be that much value. So if I do this, I would not take away the C++. It sounds like I might start. I will, if I can make the time, I might try to release the homework, the coding portions at least, into two versions. One that is Python for those that are more comfortable with that, and one that is C++. If you already know C++, I encourage you to try to look at the Python version when I release that. I'll try to do that. I'll make that a goal for the next assignment, because it is good to learn other languages. If you already are very comfortable with Python, I encourage you to try the C++ version so that you can learn more C++. Okay. Cool. So just checking in on Zoom. Can you guys still hear me?
Yes, we can hear you.
Okay. Okay, thanks. Yeah, I think my headphones are not working today, so you're probably just gonna have to listen from, I think my laptop is the one picking up the sound. All right. So let's get started with the actual lecture, guys. Today we're actually gonna do a little bit of code review. So this is actually something you do pretty frequently. Like, a lot of my job is looking at other people's code and trying to figure out what they're trying to do and whether there are bugs or not. Okay. So let's pull this open. This is actually, so from last lecture, we covered the case select algorithm, if you guys remember. Let me zoom in a little bit so you guys can see. This is actually an implementation of case select. This is the main function. It is just calling a bunch of other functions. Okay. We're going to spend maybe 5-10 minutes just walking through the code. So this is a .h file in C++ that implements my case select algorithm. So it takes this input of reference to a vector that is const. Somebody that knows C++ want to explain to me what that is or why we do it that way? Yeah. Yep. So the const here, this means that, so this tells you what the type is. The type of this variable is a vector of integers. The const tells you that you're not allowed to change it. And then we take it in as a reference. That's a little ampersand, because we don't want to make a copy of the vector when it gets passed to the function, right? You'll see this pretty often. Also, so technically you don't need the const here, but I marked the int as a const as well. So this is in the .h file. And you'll notice in the main CPP, we include the .h. So that lets the compiler know that this function exists. In the case select CPP is where we actually implemented. So this is the implementation of the algorithm we covered in class in C++. Let's walk through it. What is this part doing? Yeah, back there. Sorry, what? Okay, so it's checking the size of the input. It's checking to see if it's less than 5. If it's less than 5, what does it do? It sorts it, and then anybody on Zoom? Come on, guys. This is the algorithm we already covered. This is the code for it. So you should know what it's supposed to do. Yeah. Right. So it takes in the values, which could be in any order. If they're less than 5, it sorts them. And then it returns the kth smallest. Right. So it's k minus 1. Right. So this is doing, it's returning it's the base case for the kth smallest, right? And if you look at the pseudo code, this is very similar to what we wrote in pseudo code, except I think I wrote like use merge sort, right? Okay. So let's talk about this. So what is, again, so this should look very similar to you for the pseudo code. Essentially, what is, somebody want to walk me through the rest of this? What is it doing? So this function, you actually don't know what it does, but the name should give you a hint as to what it's doing. Yeah. Yeah. So this, you can kind of, like, we called it partitioning in the pseudocode. So the way I wrote the code, I just wrote a function. We're going to look at it called partition. Takes in the vector, and it looks to be splitting it into a left, a right, and a pivot. Okay. You don't know what these types are, but it turns out this is a vector, this is a vector, and this is an integer. Okay. So you don't know that from the code yet, but okay. So we split it into left, pivot, and right. And then who wants to walk me through this part? Yeah. Yeah. So basically it's saying if I'm looking for the kth smallest element and the left side that I split is bigger than k minus 1, then that means my kth smallest element is going to be on the left side, right? So, if I'm looking for the smallest element, which would be 1, and on the left side, that's everything smaller than whatever my pivot was. Yeah.
If you continue to get unlucky and you don't select the median, because it's like randomized, right?
This one is, you actually don't know because we haven't looked at the partition function, but yeah.
Could it maybe 1 out of 100 times slower just because you're randomly?
Yep.
It's not completely random, educated guess, but it's still random.
So we actually talked about many different ways to pick the pivot. Yeah, if you do it randomly, you can definitely, the worst case running time of the random implementation is actually O of n squared, because there is a situation where you always pick the min and the max. You just get unlucky, and you're always picking it where it only ever splits one thing off. There is also a situation where this code ends immediately, like the best case running time, because you just get lucky and you happen to pick exactly the kth smallest, and that's where you get to this last part of the code. So if you guys look at this code and compare it to the pseudocode, it should be very similar. It's just looking at the pseudocode and then writing it in C++. All right. So this is actually this is the case select algorithm. And then the thing we've been covering for the last 2 lectures is essentially this partition function, which is how do we split the array? So going to the partition function, this is what the partition function is doing. So somebody want to walk me through these couple of lines of code? So what's the first if statement doing? Yep. Yes, so it checks to see if I'm given an empty vector, I cannot partition it. And why is that? Because the partition, by definition, returns a pivot. So the vector must have at least one element in it, right? If it doesn't have an element, I can't return a pivot to you. So I end up throwing an error. It actually never happens. What is the rest of this doing? Yep. So this line calls a choose 5 pivot, whatever that function is. So it calls a function to choose a pivot from the vector, and actually a pivot index. And then this actually grabs the actual pivot. So you can infer that this choose 5 pivot is not returning the number itself, it's returning the index into the values, right? So you don't actually know how that's implemented. Choose 5 pivot is actually the deterministic algorithm that we covered in class last lecture, where we were like, take the array, split it into 5s, take the median of medians, call yourself again, like the super complicated one, right? We're going to look through a couple of other implementations, but you can imagine as you're writing code, if you don't know how to do something, just write a function and then go implement that function later, right? Okay, who wants to explain the rest of this? For loop, what is it doing? Exactly. So it actually iterates through and it compares. There's an assumption this code is making right here. What is the assumption? Yeah. Can you speak up a little bit? Is it assuming there's always going to be value? It is not. If there are no values, the for loop does not execute, and then left and right are left empty, which is what we want, actually. Yeah.
Assuming that the vector is sorted.
It is not assuming that the vector is sorted, and we do not actually need it to be sorted. We just need to take all the, so the left is not going to be sorted. It's just going to be all the elements that are smaller in whatever order. Yeah.
I think it's assuming that the pivot point is not the end.
It is also not assuming that. If the pivot point is the end, then the right side, this part will never execute, so the right will be empty. Yeah. You can always split it up, but it is close to that. It is a little close. Yeah.
So is it assuming that there's 5 pivot points already? So you basically 5 begins?
Yeah, so it does assume that this function, ideally this function returns you a good pivot. It is kind of like assuming that for the code to have a good running time. The main thing this code is not handling is this is the part in the implementation where it assumes that all the elements are unique. Okay, because if you notice, if I had, for example, what if I had multiple copies of my pivot, right? Then everything less goes on the left, everything bigger goes on the right, but then I return the pivot. So after I return, I'll have like a smaller, like I lose the fact that I had, 5 copies of the pivot. Okay, so that would be one thing if you were to improve this out. This code would be something you want to deal with, which is like, wait, what if I'm given an array that has non-unique elements? So there can be duplicates. Okay. Does that make sense to everyone? How, like, why it's assuming that? It's like super, like, it's not obvious because it doesn't write it out. It's just something that happens. Okay. So that's basically it. This is partitioning to the left and the right, given a pivot. And then the next part that's interesting is this choose 5 pivot. So we can go to the definition. I actually wrote many different ways to choose the pivots. Okay, so choose random pivot is the one we talked about, which in practice, this is what you will use because choosing a random pivot is constant time and it's super fast to do. And most of the time it works like really well. Okay, just choosing a number at random. Choosing middle pivot always chooses the pivot that is like in the middle of the vector. So it may or may not be the median, but it always chooses the middle one. Okay. Choosing favorite pivot always chooses the pivot at the 3rd index, if there is one. Choosing best pivot actually always chooses the median. So it sorts the vector, finds the median, and gives you that as a pivot. Okay. We don't have to cover all of these, but I think the 2 important ones are essentially choose random pivot. This is the one you actually would see in real life. And this is all it does. So literally given a vector, it generates a random index from 0 to the size of the vector, -1. And then it returns that number. So it literally just uniformly picks a random value from the vector. And this is actually one of the best implementations you can do. In the worst case, you could end up picking bad pivots and it could be n squared, right? But most of the time it's pretty good. And then the algorithm we covered in class is actually this choose 5 pivot. So as you can see, this is a lot more complicated than choosing the random. Not only is it more complicated, but it actually calls itself, it calls K-select recursively. So like K-select calls this function and this function calls K-select. So they're like mutually recursive. So not only is it more complicated in code, it's also more complicated in like thinking about it. So what is, somebody want to walk? So what is this doing? You guys, this is the algorithm we covered last lecture, but actually implemented. Anybody want to start walking through, for example, maybe what these lines do first? Yeah. Okay, that's great. So again, this is why when you write code, you should try to give good names to your variables, right?
So intuitively, it makes it a lot, like if I call this A and I call this B, it might be a little harder for you to figure out what it's doing, but I'm trying to call them what I want them to be. So this vector is a empty vector, starts out of medians. So you're like, okay, here's where I'm going to put my medians, right? And then chunk is again an empty vector. That's how it starts out with. But you could imagine, oh, this is going to represent the chunks that I'm looking at. Okay. So then what we do is we iterate over our initial values and we look at each element. And what are we doing? We're filling in the chunks. So we're saying, okay, put one element into the chunk. And we keep doing that until the chunk becomes of size 5, right? And once it's of size 5, we say, calculate the median of that chunk and add it to my medians. And then reset chunk to be empty. So like I'm done with the first section of 5. You guys remember we split everything into 5s and then we calculate the median of each one. So this get median function, actually what it does is it sorts the vector and then it returns the median. Why is it okay for me to be using sort here? Why does this not make my running time n log n? Yeah. Yes, that's perfect. So I know that this function, so if you look at this function by itself, you would say the running time is n log n. Because as values gets bigger, it takes n log n time because you're sorting. But I know that when I use it, I will only ever give it chunks of size at most 5. So this could be n factorial is how I implement it, you know, and it's still constant time because my input is at most 5. All right. So going back to our code, we're here. So that's how we get the median. We push them back. And now at the end of this for loop, we have an array of medians that has all the medians we've calculated. So what do we do next? What is this? Someone tell me why this if statement is here? Yeah. Exactly. So this is the part where this is the stuff we sort of skip over lecture when we're talking about the algorithms, because it doesn't matter that much. But when you're actually implementing it, this is the thing where like the computer is going to do exactly what you tell it to. And this is what you would call maybe an etch case. Sometimes you don't fill up the chunk all the way to 5, right? If your vectors of size 7, the first chunk gets to 5, and then you're going to have 2 left over. So what do you do with that? So that's why you have to add this extra if statement to see, oh, if I still have stuff in my chunk, I actually need the median of that as well. Okay. And then the rest of it you guys should know. So what does this do? This just calls kSelect on my medians, and it's asking for the median. And why can I do that? Why is that okay? Why does that not cause an infinite loop that I'm just calling myself? Yeah. Yes, because medians here is 1/5 the size of my original vector. So it keeps getting smaller and smaller. So I will call myself a bunch of times, but eventually I'll just call it on like a vector of size 5 and I'll just be done, right? Then this is the code where you would be like, well, what this function is trying to do is it's trying to return the index. So this is going to give me the value, like the number that is my median of medians. So what you do here is you use standard find to find the iterator that points to the median of medians. And then you find where is this number inside of my values array. Okay, so again, this is an implementation detail where like in pseudocode, I just say find the index in values, right? Like the answer was 6, figure out where is that 6. That maps to these 2 lines of code. Okay, so as you guys can see, this algorithm is actually pretty complicated. In practice, instead what you would do is you would implement this, which is just, it doesn't even care what the input is, to be honest. It just needs to know that there's at most n-1, and it just picks a random number, and then you're done. Okay, cool. So that's kSelect. So let's get back to lecture. Now we're going to start covering what we call randomized algorithms. Okay, so you know why I totally get it now. I get why my earbuds were not working before. All right, give me a second. Sorry. They were actually connecting.
Okay, hey guys on Zoom, can you hear me a little better now, maybe?
Yeah, it's clear.
Okay, all right, sorry about that. Okay, let's jump. So we're gonna cover randomized algorithms in this lecture, and we're gonna finish this up on Friday. So let's get started. So a randomized algorithm is an algorithm where we make some random choice. So we saw one just now, which is like I'm choosing a pivot at random. We hope that the algorithm works. So you can imagine, so in our case, the randomness does not affect the correctness of the algorithm, right? Because no matter what pivot we choose, the way we wrote our algorithm, we will always return the right answer, right? But you can imagine there are algorithms that we'll cover later in class where the randomness actually affects whether you get the right answer or not, okay? We also hope that because we're doing something randomly, the algorithm is fast. For today, we're going to look at algorithms that always work, but are probably fast. There are also algorithms that probably work and are always fast. So when you introduce randomness, it helps you give this trade-off, okay? E.g., like I said, select is a random pivot. This is a randomized algorithm. It always works, always correct. You cannot get the wrong answer with this algorithm, but it is only probably fast. Most of the time it's fast. Sometimes it could be very slow. The next thing you want to cover for randomized algorithms is one question that comes up again for all algorithms. You should always think, how do I measure how fast they are? So for randomized algorithms, there's actually two scenarios. So the first scenario is you come up with an algorithm that uses randomness and you publish it. You let everybody know. Then a bad guy gets to pick your input. Okay, so he picks what gets fed into your algorithm, and then you run your randomized algorithm. Okay, so in this scenario, the running time of your algorithm is essentially random, but the bad guy cannot control what your algorithm is doing when it's picking the random values. So all the bad guy can do is give you he can try to get, what he's trying to do is he's trying to give you an input where your algorithm is going to be the slowest, but he cannot control the randomness. Okay, that's scenario one. Another way to measure randomized, so we call this the average case. This is scenario one, is called the average case runtime, where the bad guy can pick any input, but he cannot control the rolls of the dice for your algorithm. Okay. The other scenario is the bad guy gets to choose the randomness. So he can actually control what random values your algorithm picks. Not only can he give you a bad input, he can also tell you, okay, when you roll this dice, it will return 5. This is called the worst case scenario. So for the algorithm we just covered, the worst case scenario would be the one where it's O of n squared. Because even though it's random, even though we're picking random pivots, you can imagine the bad guy, because he can control the randomness, he will pick pivots such that you always split your array into like empty and then the rest of it. Okay, so that would be the worst case running time of K-select using a random pivot is O of n squared. The average case running time using a random pivot is actually O of n, but we'll cover that. Again, like I said, what's the difference? So in scenario one, your running time is a random variable, okay? So your running time, you don't know for sure what it is. It's a random variable. The only thing you can do is you can take the expected value of that random variable. Again, so I'm introducing a lot of terminology here, but a random variable is essentially something where it's like, it happens with some probability. So we talk about expected runtime. In scenario two, the running time is actually not random. Okay, scenario two, it is not a random running time. It is just the worst case running time, the worst possible. Okay. So does that make sense? We're gonna analyze a very simple algorithm that you will never use in practice, but it'll help you differentiate between these two cases. Any questions on these cases? Okay. So this is our first randomized algorithm where we're actually going to analyze its performance. What does this algorithm do? Yeah. Randomly moves around the elements of A, right? So that's what randomly permute A means. Shuffle it, like take A and just shuffle it. Okay. But what is it doing? What is the final thing it returns to me? A sorted version of A. So you can imagine this is the simplest way to do sorting, which is if you don't know how to code and you don't want to think about it, randomly shuffle A, check if it's sorted. If it's not sorted, shuffle it again. Check if it's sorted. Okay. So you would never see this algorithm in practice, but this is a randomized algorithm. Why? Because we're shuffling, right? So shuffling means the order of the elements is random. So what we're going to do is we're going to try to measure the running time of this algorithm. Okay. So again, like we said, there's two scenarios. There's a worst case running time, worst possible, and then there's an expected running time. And we're actually going to see that we're going to try to measure the running time for both scenarios. So what we're going to do is we're going to introduce this variable x sub I, which is going to be 1 if A is sorted after the ith iteration of the loop, and it's going to be 0 otherwise, right? So what you can imagine is if you write x0, x1, x2, x3, this is going to be all zeros until you get to the last one, and then it'll be 1. And then that means your algorithm finished, right? So the running time of the algorithm is essentially going to be how many x's do I have to write before I get to 1? But each xi is random. Sometimes it's 0, sometimes it's 1, right? So something that maybe you guys will take for granted or not, the expected value of xi is 1 over n factorial. The reason for this is that there is one permutation that is sorted. There is one shuffling of the numbers that is sorted. Let's assume the numbers are all distinct. There is only one way to write them where they're sorted in ascending order. That's the one. But there are n factorial possible ways to shuffle them, right? So the probability that xi is 1 is 1 over n factorial. Does that make sense?
Why wouldn't it be n factorial minus 1?
Because you want to calculate what is like, so the probability is just what are my outcomes I want? Like what are the outcomes where I'm happy over the total outcomes, right? So this is like when you flip a coin and you say the probability of getting heads is 1/2. That's because I can flip it and I'll either get heads or tails. So there's 2 total outcomes and one of them is heads. So the probability of getting heads is 1/2. So this is the same thing. Only one ordering is sorted, but there are n factorial possible orderings. Yeah. Oh, on Zoom. Sorry guys. Let me see. Is that on the chat maybe? Hey guys on Zoom. Oh, I can't hear you guys. Interesting. Can you ask on the chat? Do you guys know what the question is? No? Guys on Zoom, do you want to ask the question?
What was the question?
Okay, I'm not getting a question on Zoom right now, so we will continue. But yeah. Okay. Yeah, I've got 17 participants. If you guys want to type the question, please type it on chat. I'll try to keep that open while we keep going with the rest of the lecture. Okay, so does this make sense to you guys that the expected value of xi is 1 over n factorial? Oh. Somebody asked what the question was. Yeah, I heard that, but what is the question? Yeah. Okay. I will keep going, but please post the question on the chat. And if you guys see it, if you happen to be on Zoom, let me know. So we are here. So the expected value of xi is 1 over n factorial. The other thing you want to take for granted is that the number of iterations until A is sorted is the inverse of the expectation. So again, this is coming from statistics. You don't necessarily need to know this, but it should make sense intuitively because it's asking how many times do I need to run this for loop? It's like if you're flipping a coin and the probability of getting heads is 1/2, how many times do you think you have to flip the coin in order to get 1 head? You have to flip it 2, okay? If the probability is 1 out of 1,000, how many times do you have to flip the coin in order to see one? How many times do you think you have to flip the coin in order to see 1 head? You actually have to flip it 1,000 times in expectation. So again, it's not guaranteed you will see a head, but in expectation, you will flip it 1,000 times. So this is the same thing we did then, which is you flip the expected value to get the number of times that you have to run this for loop, this while loop. So the expected running time, so this is the expected running time. We're in scenario 1. We're trying to figure out how long is this algorithm going to take to run. The expected running time on a list of length n is going to be the number of iterations that I do times the amount of time that each iteration takes me. Does that make sense? Now, the amount of time each iteration takes me is actually not random. We're going to assume that shuffling a vector of size n takes n time, like O of n, just shuffling it, okay? So we can actually take this out of the expectation. So this becomes just a constant that then we're multiplying by the expected number of iterations, okay? Now, that is going to be O of n. And expected number of iterations, we just computed in the previous slide. We said the number of times the while loop is going to run in expectation is n factorial. So the running time of this algorithm is actually n times n factorial. So this is the first time we see an algorithm, I guess, that is not polynomial in running time. It is actually n times n factorial, which is n plus 1 factorial, but you don't have to worry about that. Or like, actually, it's not n plus 1 factorial. Forget that. But yeah.
Would it crash faster than like n squared and
Would it? This is much slower than n squared, n cubed. Yeah. Yeah. Okay. So this is a bad algorithm, but this is the scenario 1 where we're trying to analyze what is the expected running time. So in expectation, I expect my algorithm to take n times n factorial steps in order to find me a sorted array, right? So that's the expected running time, which is actually really, really big. It's really bad. You never use this. But now scenario 2 would be what's the worst case running time? So again, this is where somebody can pick the random numbers that you get. Okay. So I'll give you guys 2 minutes to tell me what is the worst case running time of this terrible, terrible algorithm. So this is like I get the most unlucky I could possibly get forever. Yeah, talk amongst yourselves, see if you can come to an agreement. So here's what the algorithm does. It has a while true loop. This is the part that's random. It'll try to randomly shuffle it. And in this scenario, we're not saying an expectation how many times it takes to get the right shuffling. This is somebody else gets to pick how the A gets shuffled. Somebody else who really hates you, like doesn't like your algorithm at all, wants to make it the worst possible. What are you guys thinking? Let me see. Let me go to the back because I feel like the guys back there maybe figured it out already. Got some ideas? Any ideas?
Would it be something like n factorial forever?
Couldn't it just go forever?
If you have to do n factorial twice, is that really bad?
That n factorial twice. I mean, it's worse than n factorial, but it's like n factorial is already so bad. I wouldn't say n factorial twice is like much worse. Yeah, if you did like n factorial squared, that would be even worse. If you do n to the n, that's even worse. But yeah. All right, guys, let's bring it back because I think I heard the right answer from somebody. What was your name? Yeah, Oman. Sorry, yeah, what's your name? Oman's. All right. So do you want to tell us what you think is the worst case possible running time? It just won't end. It'll be infinite. That is actually the worst case running time. It is infinite. If somebody gets to pick your randomness, then they can always pick the shuffling so that it's never sorted. And then your algorithm just keeps going and going. Okay. So there is a distinction in how you analyze, right? So the expected running time is n times n factorial, but the worst case running time is actually infinite. It could go on forever. Now, the worst case running time for the select is not infinite. There is, because even if you pick the worst possible pivots, your algorithm always makes progress, right? So what have we learned? We learned that the expected running time is when you publish your algorithm, the bad guy can pick the input. So he can pick a bad input for you, okay? But you are the one that gets to roll the dice, all right? And then you calculate the expected value. So if you guys want to look up some statistics, expected value is probably what you're looking at. The worst case running time is where the bad guy picks the input and he gets to roll the dice. So he tells you what random numbers you're going to get. And also, don't ever use, it's called BOGO sort. There's a Wikipedia page for it. Don't ever use it. It's terrible. But there is a randomized algorithm called QuickSort that is really easy to implement. It is almost always faster than merge sort. And it has really good guarantees. So that's what we're going to cover in the next 10 minutes. So a much better, cooler algorithm that uses randomness is called QuickSort. Okay, the expected running time of this algorithm is actually n log n. So just FYI, there is no comparison-based sorting algorithm that is faster than n log n. If anybody tells you they have a faster algorithm than n log n, it's either not, they're using something else. Like if you have to compare numbers, there is no faster n than n log n. That has been proven. Yeah, we're not going to cover it in class, but it's been proven. But for QuickSort, the expected running time is the same as merge sort. Sometimes it's worse. A lot of times it's better. Okay. The worst case running time of QuickSort is actually O of n squared. So we're going to cover how the algorithm works, but sometimes you pick the wrong pivots. And the worst case running time for our implementation is O of n squared. One thing that you guys want to keep in mind as we cover QuickSort that you should ask yourself, because this will test whether you understood what we did in the previous lectures, is the algorithm is going to look very similar to the K-select algorithm that we covered last lecture. So there is a way to implement QuickSort such that the worst case running time is actually n log n as well. Okay. And you might, it'll probably come to you when we talk about selecting the pivot and how we can pick it. In practice, though, QuickSort is the algorithm you will probably use quite often. Most algorithms, most sorting algorithms are actually a version of merge sort that once your array is smallish, it uses a version of QuickSort. They can get very, very complicated, but yeah, in a lot of cases, it is O of n. Let's continue. So we are going to start covering how the algorithm works. So what we want to do is we want to sort this array. This is a divide and conquer algorithm. So you guys should already have in your mind, maybe we're going to do something where we split the input into some pieces. We're actually going to split it into the left and to the right side. Again, very similar to merge sort, very similar to K-select. A lot of algorithms are very similar. So you're going to keep seeing the same ideas. Okay. And you want to focus on like, what are the ideas that you're coming up with? So when you see a problem in the future, you can be, well, like maybe I can use divide and conquer. What if I pick a pivot at random and split it in half? Would that help me? Etc. So we want to sort this array. And the way the algorithm works is first, it picks a pivot and it picks it at random. All right. Then it's going to split the array into bigger than the pivot and smaller than the pivot. All right. So very similar to K-select right now. So in our example, it'll do like 7, 6, and then 3, 1, 2, 4. Yeah. Okay, my animations are a little off, but you can imagine this is what you get. So this is the partitioning step. Then what I'm going to do is I'm actually going to recurse on the left and the right side. Oh, I see. That's what I did. Okay. Okay, so this is after I partition it. The animations are bad. After I partition it, they're not in order. And then I'm going to call myself recursively, which I'm going to assume, because my inputs got smaller, they're going to be sorted. Okay, so once they're sorted, then I can put them back together into the sorted version of the original array. All right, so that's what I do. Because I have the pivot, I split into left and right, and then I call myself on the left and the right. And I'm going to assume that my algorithm does what I want it to do, which is it's going to sort those arrays. All right. We can actually look at this in pseudo code. So again, we need a base case. So if the length of A is less than or equal to 1, what should I return? Yeah. Yeah, just return the array itself. Because you're trying to sort. That's a typo. If somebody had caught that, they would have gotten bonus points. This should say return A, because you actually want to return the vector. Then what I did is I picked some x equal AI at random. So I picked some number in the array. I partition A into the left, the right. Then I call myself on the left to sort it. I call myself on the right to sort it. And then I return left, x, right. That's it. This is a sorting algorithm that is actually pretty good. Here's an implementation of it, if you guys want to see it in real code. Yeah.
On the previous slide, I saw the number that was in the right place. You can just go to the previous slide.
Like a bug you want to report.
I just want to see something.
Yeah.
Yeah, why is 3 on the left side?
3 on the left because it's smaller than 5.
Oh yeah, it isn't. Okay.
Yeah. So all the ones smaller than 5 go here, all the ones bigger go here. And then I call myself on this side, which I'm going to assume sorts it. And then I call myself on this side, which sorts it. So that's why they are now sorted. But originally they started out like this, where they're not sorted, and then you sort them. If you guys do want to, so we have 3 minutes left. That is QuickSort. That is the entirety of the algorithm. The question you should naturally ask yourself is, does it work and how fast is it? Those are always the questions. Actually, I already gave you the answers. Yes, it always works. It will always sort your array. Intuitively, maybe you can imagine why. Sometimes it's O of n squared. Most of the time, it's O of n log n. But for a lot of cases, it's O of n. And this is, again, this is the implementation of QuickSort. So again, I put my little source here. This code is actually copy pasted from the Stack Overflow question, because I didn't know how to generate a random index, so I had to Google it. All right. So choose pivot just generates a random number between 0 and n minus 1. Right. So that's what we said for choosing pivot. And this is, let me zoom out so you can see all of it. This is the implementation of QuickSort based on the pseudocode that we have. So again, our base case, if our array is too small, I immediately return. I'm done. Then pick a pivot at random. Then iterate through the elements. If the element is smaller than the pivot, put it on the left. If the element is bigger than the pivot, put it on the right. Question, what is this code assuming?
All the numbers are different.
Yes, this also assumes that all the numbers are distinct. As a challenge to you guys, it might be interesting to try to think, how would you make it so that if I do have duplicates in my array, this still works? Then, like I told you guys, I call QuickSort on the left, and I get a sorted version. I call QuickSort on the right, and I get a sorted version. And then I just put them back together, where I start with the left, I put the pivot after it. So I add the pivot, and then I iterate over the right, and I add all the elements from the right. And then I return that.
Couldn't you just put like, if the element's the same, can you just put like a less than or equal in either the left or the right? So like it's less than or equal to, let's say you have multiple 5s, it'll just put on the left 3 times. Is that a fix for it?
Yes. Yes, that is a fix for this one. Because the way you pick the pivot doesn't matter. Yes, that will work. So you could do this and then that fixes. Except, okay, so you have to do this. You have to do less than or equal to, and then you would avoid doing this, where you add the pivot again. Because if you keep this line and do this line, then now your array actually gets 1 bigger each time. Yeah, but yeah, cool. Right, so we're at 12:50. That is QuickSort. Next, on Friday, we are going to analyze how fast QuickSort is, but you guys actually already know all the answers to those. So thanks for coming. All right, everyone on Zoom, thank you. Hopefully that made sense. I will mark these as skipped. Cool. All right, see you guys on Zoom. I'm gonna end the meeting.